Okay, so before I start talking at you, are there any questions, concerns? Yeah, and the written assignment, I mean, most of you nailed it pretty good. A few of you were struggling a little bit with the second one. The lesson that I wanted to emphasize for that is that even for just the basic model, and this is true for all models, there's no one right way to do it. I mean, there are multiple ways of just even configuring the state space, the state variables. So just for our simplest example of the multiple server queue, we've seen, the initial one where we had states for number in the queue and the number of available servers. And then we saw that, well, instead of number of available servers, we could have instead the number of busy servers. And actually, instead of all of that, we could just have one state variable, which is just how many are in the system. That was the challenging one. And the thing is that as most of you saw, and if you didn't, if you missed that, the quote solution is uploaded. So again, it's not that there's any right one. There are multiple ways of doing the same thing, and there are lots of wrong ones. So there are unfortunately many more wrong ways of doing it than there are right ones, but there isn't just one right way. And that's as we go on, and I ask you to do more and more formulation problems, you have a certain leeway. In other words, for me, I might have a certain way of describing the states and other things. And if you come up with a different one, which is equally correct, then that's fine. So in other words, you're trying to capture what is in the problem description, or if we're modeling it out there, so to speak, you're trying to capture the essence of the thing that you're trying to model, not try to sort of get none of this is predetermined, is the point. And that's what makes the modeling part of this the most challenging piece, because it requires some creativity, it requires thinking. The part that ideally doesn't require thinking is turning it into a program. That's the whole way that these two pieces of software were designed are to minimize the amount of thinking you have to do when you have a model and you want to simply implement it. So when I say don't think, what I mean is you're just translating. So if I have an event, it goes into a method. If I have a state variable, it goes into an instance variable, a parameter instance variable. Scheduling, the way it gets called depends. So in SimKit, it's wait delay, and the Python version, it's schedule. Because I wrote the Python version after the Java version, I was able to get better names. So yes, question.
Sure, you mentioned last week the Rosetta Stone for SimKit. Is that in the resources?
That is in the discrete event simulation modeling. I think it's section 8, the first page on that. I think I promised I would upload a separate page of that, but I neglected to do so. But thanks for reminding me. For those remote, I was reminded that I'd promised to upload a Rosetta Stone for SimKit, and then for those of you using the Python, there's one for that as well. So I will upload those. I guess one of the perks of being here as the instructor instead of there is that I get to sort of fudge the deadline. So it just comes with the territory. Okay, so on to today's topic. Now, can For those remote, can you see this?
Yeah, I'm seeing it.
You see it? Okay, that's. By the time the quarter's over, I think I will have figured out how to do this. So, okay, so today, basically two models, but then one additional element to our modeling, which is the use of containers, and we'll see why that came into play. But first is another variant of our multiple server queue, and that involves having two types of servers. So let's look at that. It's our basic multiple server queue situation. However, what we notice is that we have two types of servers. Two use cases of this come to mind. One is from where the servers are machines. In one of the machine shops I used to work in my misspent youth, for a particular task, and I forget the exact task what it is because it was so long ago, but it's like, they had two different types of machines that did the same thing, and one was newer and worked faster. Everybody wanted to use that one. And the other one was slower, and nobody wanted to use that one unless they had to. Another use case might be if you had, let's just say you had the servers are people, but maybe they have significantly different levels of training. So maybe you have one set of servers who they're experienced, they've been around a long time, they're really faster at what they do. The other are relatively newer hires. They have less training, less experience, and so on average, they're going to be less adept at the other. So that's sort of the idea. We have the same task, they do the same thing, except that they have different service distributions. And as with the machine shop, so the customers just arbitrarily prefer one type over the other. Why? Because they know which ones are the good ones. And so the idea is that now the assumption is going to be that if you come in, if I'm a customer, I want one of these type 0 servers to be processing me. But if they're all busy, I'm not just going to sort of sit around twiddling my thumbs waiting for them. I'm going to get service from the other ones that are not going to be available. And that's what was happening in the machine shop as well. It's like when a part came in for processing and there were the zippy machines available, they would try to use that. If all the zippies were busy and the clunky ones were available, then you'd use that instead of just having them sit idle. Because if what you're going to do is only accept service from the good ones, then you might as well get rid of the other ones. Right? So, okay. So now let's model this. Now, first of all, we have in terms of parameters. Well, now going forward, for the most part, not exclusively, but because if we're in a situation where an arrival process is an appropriate model for customers arriving, then we don't have to include that in our description. We are not going to include that typically. So I don't have to worry about the inter-arrivals. Why? Because I can always have an arrival process and then listen to it and stick it in. So that's what we're going to do here. But okay, so in terms of parameters, I have two types of servers, and so I'm going to have two different parameters for each one. Right, so fairly straightforward. And I'm going to have two different service times. So that's what distinguishes them, is the service times. And now in the formulation, there's no, it's not built in that the service times for the preferred servers are necessarily better or worse than the other ones. That's completely up to when you stick a parameter in. And just by way of emphasizing that, I hope you're noticing that as we define these models, the description of the model does not typically specify what the probability distribution is. In other words, you want to make it as generic as possible. And by doing it this way, this gives you much more leeway in terms of when you actually want to run it and be able to use it in different situations. Because in one situation, for example, the service times you might be like a gamma distribution, but in another context, they may be a Weibull distribution or a uniform distribution or something else. If you put that into the model, if you bake that into the model, you're going to get a different model every time you change probability distributions. And this may, it may not sound like a big deal, and in these days it may not be, but back in the day, most, like when I was sitting where you were and they would formulate a model, they would always put in the assumption about the probability distribution. They would bake it in. And I never liked that. So when I got to decide, I said, okay, we're going to throw that out the window, give you complete flexibility. Okay, now state variables. We still just have one queue here, but like if you remember, we had a tandem, well, when we had the tandem queue, we had 4 different state variables. We had available servers and queue for each of the 2 stations. Now we just have one queue. It's not tandem. It's all in one bank. So we only need one variable for the number in the queue, but we need to have separate number of available servers for each of the 2 types of servers. Okay, so again, we're just following our nose down the assumptions in the model. And so my recommended way of kind of dealing with moving from the state variables to the events is pick a state variable and identify when it could change and how. So we can always start with the run. So this can always be done immediately. So for the number of customers in the queue, well, we have an event. We've often called it arrival, but we can call it anything else. I mean, there's nothing about the word arrival that makes it an arrival. What makes it an quote arrival is this state transition. So if we called it Irving and had this state transition, it would still act like an arrival. So just like naming variables and methods in a computer program, you want it to be as self-documenting as possible. So arrival is a good name for this because it describes what's happened. And like all of these they are not because they are laws of nature, but because they're descriptive. So now what are the other ways that the variable queue can be modified? Well, one is when the customer starts service on a type 0 server, and the other is when they start service on a type 1 server. And that's what these are. So I need 2 different events because they're gonna, well, for queue, you might think, well, maybe I only need 1 event because there's only 1 queue. But then when we move on to, say, pick the number of available servers of type 0, then what could cause that to change? Well, when it starts service on a server of type 0 on a customer, or when we end service. And what do? I lose a server when I start, I gain a server when I finish. And these are not parameters, remember, this is all part of the name. Okay, so just be careful about that. And then similarly for the number of available servers of type 1, we either start or we end. So in terms of the state transitions, these are the, again, they're, especially in larger models, there's always kind of it's not linear. You kind of always have to kind of realize later, oh, shoot, I forgot something. but for a small model, this is where we're pretty much finished. Now the tricky part then is now how do we do the scheduling? Okay, so now because we're going to be listening for an arrival event, then the run is not going to schedule anything. And so typically for our server components, when it's a server component, we're usually not going to schedule anything from the run unless we have to. In this case, we don't have to. Okay, so well, let's pick off the easy ones. So when I start service on a server of type 0, I could schedule an end service, and my delay is the service time of type 0. And I have the similar thing for type 1. So this is the easiest one to do. Okay, so I definitely have that. Now what about when I finish service on a customer of type 0? Now we have to be a little careful about what we actually check. So now there's a server of type 0 available, and that's the preferred one, of course. What are they going to worry about? Are they going to stay idle, or are they going to serve a customer? They're going to serve a customer if there's somebody in the queue. So this is, again, this is you say, well, this is right out of the multiple server queue thing. But you need to be a little careful. And when we let's see, I won't do it, it's not today, but when we turn this around and actually have two different types of customers, then we have to kind of worry a little bit. And it's the same thing here. So it's like if there's somebody in the queue, the condition is the same, then we're going to schedule another start service there. So these are the easy ones. You know, again, just like when you take a test, always do the easy questions first because you'll maximize your score. Likewise here, it's like once we start having an event graph that is starting to take shape like this, then it's something happens. Okay, but now comes the tricky part. What is the arrival event possibly schedule? Well, could it schedule a start service on a type 0 server, assuming the S0 server is available? So, and we can express that by this expression here. So the thing you hear me say a lot, because it bears repeating, is that there are two ways of describing things in our model. One is using English or your favorite language. In other words, a descriptive form of it. And the other is the language of the model itself. So in this, an arriving customer can start service on a type 0 server if there's an available type 0 server. So this expression translates the English sentence, there is an available server of type 0. And vice versa. So this expression translates back into English. And why is that important? Because if you're trying to describe the model or brief the model about what it does, you will typically be doing it to people for whom this is just a bunch of circles and arrows and doesn't mean anything. And and if they're kind of savvy, they'll kind of look at it. And one of the nice things about event graphs that I found is that with a little bit of prodding, people kind of see how these things work roughly. But if somebody says, "Hey, now what does this do? Why, can you explain what that?" Oh, well, that's S0 bigger than 0, and well, that's not going to land. Say, what does this mean? This means if there's an available server, then we can schedule a start service right away of that type. Okay, so now things get a little tricky. So now if we were to to just kind of blindly follow ourselves, we could say, well, we could start service on a customer of type 1. And it gets, so if we're just kind of, if we're just kind of blindly following our multiple server queue, we could write something like that. So, and it makes sense that if an arriving customer will start service on a server of type 1 if there's one available. Kind of makes sense. Now, how is this model going to behave as it sits? Close. The way this is going to behave is this, if there are both types of servers available, it will schedule them both. That's what it does. There's no randomness here. In other words, the rule is for every scheduling edge with a true Boolean condition, that event gets scheduled. So if both of these are true, then we got one customer who we cut in half and sent, or the same customer is at 2 different servers. Okay, so now is that reasonable? No, that's not. So what is the rule? The rule is that if the server is available, a type 0 is available, they'll take that one. So this is the only condition we need. But what is the condition under which we will start service on a type 1? Exactly. Or there isn't any of, there are no type 0 servers available. And how do we express that? By saying S0 must equal 0. Okay, so this is, so the lesson is that these I've said this before, but it bears repeating. Event graphs, like computer programs, are stupid things because they do what you tell them to and not what you want them to. So you want to, try out, just do some thought experiments on these. In other words, okay, so what happens if there's an arrival and both are available? Well, now, if they're both available, then this condition is true, and this condition is now false, because if they're both available, S0 is positive. And so this is an and so false, true. And just in general, if this is if you're in a situation where one event can only schedule one, then it's basically like that if that we did a couple times ago. So in other words, the 2 scheduling conditions need to be mutually exclusive. Okay, and that's hopefully what the final one looks like. Yeah. Yes. Great question. So the question is, what if we have an N service 0 event and an N service 1 event at exactly the same time? Now, as long as we're using continuous probability distributions, that's not going to happen. That's where we would add a slightly higher priority. Remember, we had 2 levels of priority here. I would add sort of a higher priority to that and a high priority here. And so what that would do is, if they happen at exactly the same time, then this would schedule, and this would schedule with a higher priority, which means that because it's happening at the same time, this one would kind of be waiting. And so when it would go to schedule it, then it would queue, it would already have grabbed queue. Yeah. Yeah, you'd probably have to, kind of do this thing here and leave this at the default. if that's an issue. I mean, as I said, in 30 years, I've never had continuous distribution. You know, for these models, use continuous distributions, because in those cases, it's just the probability of happening is virtually zero. You know, and the only non-zero part is the digital business of the computer. But this is, you know, it's a good observation, because that's something which does occasionally come up. Okay, now the other interesting thing. Okay, let me just kind of do it from. The interesting thing is that when you see events that are kind of almost pretty much the same, like the start service 0, there's like the 0 kind of shows up here, and the end service 0, the 0 shows up here, and similarly the 1 shows up here and the 1 shows up here. And what that kind of suggests is that there may be a way of combining these into one event and make it an argument. And that's basically what this does. And it is kind of messy, but in other words, if I use arguments, I notice that the start service event is basically the same for each, but the sort of the number matches the number in the state transition. And so that allows me to make the start service event with an argument, and then I can simply apply that argument to my number of available servers. And similarly with the end service event, because if it has an argument, I can make the number of available servers be indexed by the argument. And now the only issue now is that I need to make sure that I pass the right things. So if I start service on a server of type I, then that I will tell me what the service time is, but I need to pass that I to my end service event so it knows which I to use for its state transition. And because if I finish service on a type server, whatever type of server it is, I may schedule a start service on the corresponding one. And so I need to pass the parameter. Since I'm using arrays, I can use my for loop initialization here to initialize them. And the tricky part comes now with the arrival, what happens with the arrival. And here the most straightforward way to do it is, I see, because the scheduling edges, I now have 2 different conditions on the scheduling edge, and that means that I need 2 different scheduling edges. So here, if there's an arrival and there's an available server of type 0, then it'll schedule start service passing it 0. But if there are no 0s available and a 1 available, I can schedule a start service and pass it a 1. So these are 2 entirely equivalent models. Is there an advantage to one or the other? Well, maybe. Here I have fewer events. On the other hand, the part of the guy who invented these, actually one of his motivations, and this was something I actually worked on for a little bit, was can you take a model and create an equivalent model with fewer events and prove that they're going to be the same model? And why? Because back in the 80s, computers were still pretty minuscule certainly by modern comparisons, and so the idea of having fewer events in the model was desirable. So in other words, this was preferable especially because you didn't even need this init thing. You kind of do all these by hand. So instead of 5 events in the key part of the model, you only have 3. So we've kind of saved ourselves 2 events. In my experience, I've come to complete opposite conclusion. I prefer models that have more events that do smaller things. So for me, now these are equivalent things, and I think it is important to be able to kind of parse this and understand what it's doing. But the thing that makes the execution of simulation models slow down is not the number of events in the model, but the number of events on the event list. And these 2 models will have exactly the same number of events on the event list. So 6 of one, half dozen of the other. Anyway, okay, so, and then the listener, we have an arrival process and the server component. So whether it's this one or this one, we have arrival events with no arguments, and so an arrival process will be able to drive it. Okay, so now I want to talk about containers. For containers, I mean, you think the data structures, the Java collections framework. Python has a little bit less in terms of that, although there are extra libraries you can use. But even the basic one of Python turned out to be usable enough. So this is an extension beyond the original event graph models only had scalar data. But we can use containers, and that turns out to be a very useful thing. So for example, we can have a state variable, which would be a first in, first out queue. Now queue, this is not the queue of customers. This is a queue in the data structure sense. And sort of the most straightforward way is a container containing the customer arrival times. And then they're first in, first out. Okay, why might we want that? Well, maybe you don't trust Little's formula. Or maybe you want other measures besides just the average. So as in the basic server model that we've had so far, we cannot explicitly tally the customer times. When you did your first assignment by hand, you had to do a lot of thinking in order to do this. You had to say, okay, this guy came in at this time and then left at that time. And then this one came at this time and left at the other time. Whereas for the time varying ones, all you needed was the state transition, you just needed the previous value and the times. And so a statistics object, which you will actually be using in this week's computer assignment, can simply listen to those state transitions, which in Java would be property changes and in Python are state changes, and then compute the time varying means accordingly. But you would need to use Little's formula to do the explicit tally. But what if you didn't trust that? What if you wanted to explicitly tally the customer times? Again, we're in multiple server queue. We're in a component framework, so we don't have to worry about arrivals just yet. So our parameters are just going to be our 2 usual suspects of service times and number of servers. And so in terms of state, the first state is going to be our usual number of available servers. We'll stick with that. We could have used busy servers, and I'll leave it as an exercise for the disinterested student or the board student to kind of see what it make. But the other state now, instead of our capital Q, I made this a lower Q just to distinguish it. And this is a FIFO first in, first out container of the arrival times, and its initial state is empty. So this is a state variable in all the forms of the word. And we're going to add 2 additional states, which are going to be non-persistent. These are transient states. In other words, I want the delay in the queue, that is time, the actual times that each customer spent in the queue, and I want the time that the customer spent in the system as explicit variables. I want those to be explicit. So now how can I do that? I can't do that with our basic simple server model, but I can with this, as we'll see. So the number of available servers, this is a time varying state. So we've distinguished time varying means versus tally means. And where that connects with state variables is that we have states that are time varying states, and those are the number of available servers and this queue. Its quote value is the contents, but if we know if we have access to our container, we know how many are in it. That's the thing we're really interested in. But the delay in queue and the number and the time in the system, these are tally state variables. And that means that we're going to estimate those the usual way, which is we add them up and divide by the number. Okay, so now let's look at events on this. So now we're going to have some manipulation of this first in first out queue. So our run event, we're initializing these guys. Now these transient states are always gonna be sort of not a number. You know why? Well, in the beginning, before anybody arrives, how many available servers are there? Well, we know what that is. In the beginning, how many are in the queue? Well, we know what that is. In the beginning, before anybody arrives, what is the delay in the queue? Undefined, in other words. How much time was in the system? Again, undefined. So our initial values are going to be not a number. And so, hence our run event. Okay, so now let's take our state variable Q, the FIFO thing, and now the thing is that in one of the few keywords in event graphs is a sim time. You've already seen sim time in both the Java and the Python ones. That's something that the event list or schedule knows about. And so when a customer arrives, what we're going to do is we're simply going to add the current time to this container. So in a way, we're going to kind of shadow the physical customers by their timestamps in this other view. Now, what happens when, what else happens to it? Well, a customer can be removed from it. And if the queue itself for the customers is first come, first serve, then the queue, the one that we remove is going to be the one at the top. Now that's the traditional, the original name for something like this was to pop. The actual name that you use in the code is going to be a little depend on your language. But we're going to pop that off and we're going to kind of save it to this local variable. But now the current sim time minus the time, what is that time? That's the time that that customer actually showed up. And what's the difference? The difference is how long they were in the queue. And that's what you did by hand. If that, I forget if I asked, maybe I didn't ask for that, but if I had, then that's what you would have done. And then we also lose our server. So now the end service, now here's the kind of issue is that the end, I want to be able to do the same thing for the end service event, because that's going to signal that when a customer actually finishes their service. And so the difference between the time at which that occurs and this other value is going to be how long they were in the system. the thing is I need to tell it what that is because it's not, that's not in the queue anymore. And I need to remove it from the queue because if I leave it in the queue, then it's going to look like they're still in the queue. So how do we kind of fix that? Well, as before, if there's an available server, I can start service. Okay, now when I start service, though, I can schedule an end service after a delay of a service time. But now, and this is something to always check, if I'm scheduling an event that requires an argument, I always need to have a parameter to pass. Just as if I'm invoking a method that requires an argument, I need to give it that value. And what value can I give it? I can give it this value right here. Well, what is that? That's the time that this customer actually showed up. That is the time at which their corresponding arrival event occurred. And so when I pass that to the end service, that will tell me the time in the system for that particular customer. And now just the final, now the condition, remember our original condition was Q bigger than 0, but I can't, that has no meaning for a container, but if I'm not empty, empty, that should be a P. So the condition now is that Q is not empty. Or, yeah. So this is the final model, and sort of add the priorities there. So okay, a couple things here. So this gives us the capability of kind of saving information in a container. Later in the course, we'll actually we'll look at situations where every server is actually a little bit different, and so there may be a container of servers, so that when we that would be a next logical step in this. But here's the thing now, is that and this was another thing that that caused me angst when I was taking the comparable courses that you're taking. All the models baked the statistics into the model. In other words, if you wanted to collect the mean or the standard deviation of something, that was baked into the model. A while back, I had actually it was one of my thesis students was using a simulation of record for in this case it was for the Army, and they and there were some measures they wanted to get from it, and the developers had not been interested in those. So the student could not get the measures that he wanted because the developer hadn't put them in. And that was, well, annoying to say the least. And coupled with my angst about the difference between having the logic of the model and the statistics of the model, I wanted them to be separate. So that is why in these models, there are no statistics. Now, does that mean that you can't collect any statistics for that? Well, if you've done the second assignment, you'll know that that's not true. Okay, so now how does that work? Well, if you remember in the implementation, every time there's a state transition, there's this, you notify things. In Java, it's the property change, fire property change. In the Python, it's called notify state change, a better name. But what that does is that sort of sends out into the ether the notice that this state, which is the first string, the name, has changed value. and this is the new value. So what that allows you to do is have these statistics objects be listening for those and doing the computations. So in the simple server that you're doing for the current assignment, it is listening for a time varying average. And for this, if I wanted the, say, the average, if I wanted statistics on the delay in the queue or the number or the time in the system, there would be a tally object, which would be logically identical to the ones that those of you who had the Java course previously, if you remember, you kind of wrote one, you know, where you took in a value one at a time and then updated your counters. Logically, that's something like that is happening both in the time varying stat that you're using for the current assignment and will be for the tally stat that you're going to use for the next assignment. What that lets you do is simply put in the state transition. So in other words, this state transition, when you implement this, this will fire a property change or notify a state change that this delay in queue has changed value and what the value is. And so one of you just imagine a statistics object listening for that, and when it hears it, it updates its counters. And at least those of you in the Java course, you know exactly how that was done. Something similar is going on in the time varying one. It's a little bit more complicated, but logically it's exactly what you did in that first written assignment, where it keeps the old value and then figures out how it has to save the old value in the last time. And then when it hears a new one, it takes the old value, computes the amount of time that's elapsed, adds that to the running total, and then updates to now the old time is the new time and the old value is now the new value. So the next time it hears it, it updates it accordingly. So logically, it does exactly what you did in that first assignment. So what we can do now is, well, we can now explicitly tally these things. And that's there's now a very short step to the next level of that is which not tomorrow but the day after we're actually going to have objects, because sometimes there's more information that you might want to have about the customer. In other words, the simple server that you're working with now and that we've been doing in various forms has no information about the individual customers. They're just a count. But what if you want information about those individual customers? Well, in an object-oriented world, we can represent those as objects. And guess what? That's exactly what we're going to do day after tomorrow. Okay, so, and then now for your edification, another written assignment has been posted. The first problem is, now these are a little more challenging than the ones I've been giving you, just so you know. The first problem is one you should be able to do, but it'll require a little bit of thought. The second one, I would advise you to wait until after tomorrow's class, because I'm going to show you a model that'll be a little baby step toward that. Okay, now, are there any questions in the room or remote? If not, then we'll see you tomorrow. And the next computer assignment is due close business today. Any issues with GitLab or anything, let me know. Excellent.